S-block elements. S-block elements are located in the extreme left side of the periodic table. In the extreme left side of the periodic table, we have two columns, two groups. Group 1 and Group 2. Group 1 and Group 2 elements together called S-block elements. The elements are lithium, sodium, potassium, rubidium, cesium, francium. Group 2 elements are beryllium, magnesium, calcium, strontium, barium and radium. Out of these elements, francium and calcium are radioactive. Lithium family. Each group is known by the first member. This group 1 is also known as lithium family. Group 2 is also known as beryllium family. Group 1 and Group 2 elements together called S-block elements. Why are they called S-block elements? Because the last electron in these elements, last electrons are present in S atomic orbital. That is valence electron present in S atomic orbitals. That's why the name S-block elements. The general electronic configuration of Group 1. Group 1 elements have general electronic configuration NS1, only one valence electron. Group 2 elements have general electronic configuration NS2, two valence electron. Because they contain only one or two valence electron, all these elements are very reactive. Group 1 elements are also known as alkali metals. Because all these metals, when dissolved in water, they produce strong alkalis. When dissolved in water, Group 1 elements form strong alkalis. Group 2 elements are called alkaline earth metals. The oxides and hydroxides of Group 2 metals are alkaline in nature and they are found in earth's crust. That's why the name alkaline earth metals. So NS1 is the general electronic configuration of alkali metal, NS2 the general electronic configuration of alkaline earth metal. So general electronic configuration of S-block element will be NS1 to 2. 1 or 2 valence electron. All the members of a group exhibit similar properties. So all the alkali metals exhibit similar properties except the first member, lithium. Similarly, all the alkaline earth metals, that is Group 2 elements, show similar properties except beryllium. The first member in every group show properties different from the other members of the group. Here lithium show different properties. Beryllium also is different in properties from other members of Group 2. This anomalous behavior shown by first members is due to their small size, exceptionally small size. The first members in every group are exceptionally small in size. They have got a high charge to radius ratio. They possess the highest ionization enthalpy in a group. They possess highest electronegativity in a group. They do not contain d atomic orbital in their valence shell. So all these make these members to behave differently from the other members of the group. Moreover, lithium, the first member, lithium show properties similar to magnesium. That is, lithium shows similarity with the magnesium. That is second member of Group 2. This type of similarity between the elements which are placed diagonally in the periodic table. See, lithium and magnesium. We can say these are placed diagonally in the periodic table. Lithium shows similarity with the second member of following group. This type of relationship is called diagonal relationship. This is an example. Lithium shows similarity with the magnesium. An example of diagonal relationship. Similarly, beryllium shows similarity with the second member of group 13. The second member of group 13 is aluminium. Beryllium shows similarity with the aluminium. Another example of diagonal relationship. The reason for this diagonal relationship or similarity between these pairs of elements is because of their similar ionic size. We know that when we move from top to bottom, down a group, atomic size increases, right? But when we move from left to right, atomic size decreases. So what happens when we move diagonally? This increase and decrease in the atomic size, the effect get cancelled. So lithium and magnesium show almost similar size and hence they exhibit similar properties called diagonal relationship. Dear children, let us now explain the atomic properties of alkali metals, that is group 1. So let us write the group 1 members again. The group 1 members are called alkali metals. All the S block elements are metal. These group 1 elements are called alkali metals because when they dissolve in water, they form hydroxides which are alkaline in nature. The members are lithium, sodium, potassium, rubidium, cesium and francium. Here francium is radioactive. Lithium atomic number 3. Lithium, the electronic configuration can be written as after helium concentration. After the noble gas configuration helium, then comes 2s1. This is the configuration of lithium. Sodium atomic number 11. After the neon configuration, 3s1. Potassium comes after argon configuration, 4s1. Rubidium also coming after the noble gas krypton, 5s1. Cesium after the noble gas configuration of xenon, 6s1. Francium has got the configuration of radon, noble gas radon, then followed by 7s1. See, the outer electronic configuration of all the group 1 elements are similar. 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. Outermost s orbital contain 1 electron, 1 valence electron. So after losing this valence electron, they can attain the stability of stable noble gas configuration, right? So these elements have strong tendency to lose 1 electron. They readily lose 1 electron and form monovalent positive ions. Lithium form Li plus ion. Sodium form Na plus ion. After losing their valence electron, they form monovalent ion. Potassium forms K plus. Rubidium forms rubidium plus, etc. So they have strong tendency to lose 1 electron. Why? Because after losing 1 electron, they get the stability of stable noble gas configuration. So alkali metal, group 1 metals are very reactive. Chemical reactivity is very high. Group 1 metals are the most reactive metals in the periodic table. These elements, because of their reactivity, they do not find in free state in nature. Group 1 elements are found in combined state. Now let us compare the atomic and ionic size down the group. Down the group, how the atomic and ionic size vary. Atomic size down the group. Down the group, atomic size increases. Because the number of shells increases, distance from the nucleus and the outer electron increases. So atomic size increases down the group. Right? Atomic size increases. Lithium the smallest alkali metal, francium the largest. Now ionization enthalpy of group 1 elements. We know what is ionization enthalpy. Ionization enthalpy is denoted by delta Hi. It is the energy needed to remove the most loosely bound electron from an atom. That is the energy needed to remove the valence electron from an atom is called ionization enthalpy. Because they have strong tendency, only one valence electron, and they have strong tendency to lose that electron, only small amount of energy needed to remove the valence electron from alkali metal. Means it is easy to remove, they readily remove their valence electron. That means alkali metals have low ionization enthalpy. Because of their low ionization enthalpy, they are very reactive. They readily lose electron, only small energy enough to lose the electron from an alkali metal. They have low ionization enthalpy. Now down the group, how ionization enthalpy vary down the group. Down the group we know atomic size increases down the group, right? What about the nuclear attraction on the valence electron? Nuclear attraction experienced on the valence electron down the group decreases because distance from nucleus increases. Atomic size increases, no? So distance from the nucleus increases, nuclear attraction on the valence electron also decreases. So the removal of electron becomes easier and easier when we come down in a group. That means ionization enthalpy decreases. Down the group, ionization enthalpy decreases. Clear? This is due to increase in the atomic size and decrease in the nuclear attraction down the group. Now, the ions produced in water are stabilized by a process called hydration. Just now we told these readily lose electron. Let M be an alkali metal. An alkali metal atom readily lose one electron and form metal ion, monopositive, monovalent positive ion. Means lithium forms lithium plus ion, sodium forms Na plus ion, potassium K plus, rubidium plus, cesium plus. And when an ion is produced in water, this ion, for example, if you take lithium, this positive ion will attract water molecules around it. The attraction is between the positive charge on the ion and the negative pole of the water molecule. Water molecule we know polar in nature. There is a positive and negative pole. OH2, I am writing it as OH2. Oxygen end is partially negative, hydrogen end is partially positive. Water molecule is polar. So there would be attraction between the positive ion and the negative pole of the water molecule. So a number of water molecules are attracted to it because of the attraction between the ion and the negative oxygen atom, oxygen end of the water molecule. Means a number of H2O molecules are attracted. H2O molecules are arranged around the lithium ion because of the attractive force between negative end of the water molecule and this positive ion. This process is called hydration. If the solvent is water, it is called hydration, or generally we say solvation. So when an ion is produced in a solvent, solvent molecules are attracted towards it. The ion attract the solvent molecules. Here this type of attraction is called ion dipole interaction. Water is a dipole, so the attraction between ion and dipole, ion dipole interaction. This process is called hydration. During hydration, energy is released. Energy is released. That means hydration stabilizes the ion. The amount of energy released during the hydration is called hydration enthalpy. What is hydration enthalpy, children? Hydration enthalpy is the amount of energy released when an ion is hydrated. During hydration, energy is always released. That amount of energy is called hydration enthalpy. This hydration enthalpy depends on size of the ion, size of the positive ion. Smaller the ion, greater the hydration. That is, hydration enthalpy vary inversely with the size of the ion. Smaller the size of the ion, greater the hydration enthalpy. So which alkali metal ion is mostly hydrated? Hydration enthalpy is maximum for the smallest ion. Which is the smallest ion? Lithium. Lithium ions are mostly hydrated. More hydrated than sodium, which is more hydrated than potassium. This is the order of hydration enthalpy. This hydration enthalpy is denoted by delta H with a subscript HYD. Hydration enthalpy. Hydration enthalpy down the group decreases. As the size of the ion increases, hydration enthalpy decreases. That is, lithium is mostly hydrated. Maximum degree of hydration in the case of lithium because of its smallest size. Now when we coming to the physical properties. Physical properties of alkali metal. All alkali metals are silvery white in color. They are all soft. They are light metals. When we compare the size of alkali metals with the other elements in a period, alkali metals have the largest size in a period because from left to right atomic size decreases. So in a period alkali metals have the largest size except noble gases. And all the alkali metals are soft and light because they contain only one or two valence electron. Only fewer number of valence electrons present in them. Hence, their metallic bonding will be weak. They have weak metallic bonding. That's why they are soft. And they have got melting point. Because of weak metallic bonding, they have melting point and boiling point very low. Low melting point. And another important property of alkali metal is that they can show characteristic color in the flame. When alkali metals or their salts are shown in a flame, they give characteristic color. Lithium give crimson red color. Potassium salts show violet color. Sodium show yellow color. Rubidium show red violet and cesium give blue color in the flame. So they can be detected from the color shown in the flame. That is a chemical test to distinguish or to detect these alkali metal ions, which is called flame test. They give characteristic color in the flame because when these metals or their salts are shown in the flame, the valence electron, they contain only one valence electron. Alkali metals we are discussing about now. So the valence electron present in these alkali metal get excited. They absorb energy from the flame and get excited to higher energy level. Higher energy levels are unstable, so the electron return back emitting energy. That emitted energy corresponds to the color of crimson red in the case of lithium, violet in color in the case of potassium. Yellow region in the case of sodium. That's why they show characteristic color. When light falls on this metal, because their low ionization enthalpy, they contain only one valence electron which can be readily removed. When light falls on this metal, they absorb light and lose their electron. So the energy of the light is enough to lose an electron from an alkali metal. Hence, these metals, especially cesium and potassium, are used as electrodes in photoelectric cells. These are used as photoelectrodes because when light falls on them, they can produce electron. So these are used in photoelectric cells as photoelectrodes. Now coming to the chemical reactivity. Chemical reactivity or chemical properties of alkali metals. Alkali metals are very reactive. They react vigorously with the atmospheric oxygen and also with the water. With the oxygen they form oxides. In water these oxides further react with water and form hydroxide. Lithium when react in oxygen form monoxide. Lithium monoxide is produced. Monoxide. Sodium react with oxygen and form peroxide of the formula Na2O2. This is a peroxide. Potassium, rubidium and cesium. For example, potassium when react with oxygen we get KO2. This is superoxide. Similarly, rubidium gives rubidium superoxide, cesium superoxide. We know in normal oxide, that is lithium oxide, oxygen show normal oxidation state of -2. But in peroxide, oxygen show an oxidation state of -1. In superoxide, oxygen show an oxidation state of -12. These metals react vigorously in atmospheric oxygen and with water also. Hence, these elements are normally stored in kerosene oil because they cannot be kept in air, they cannot be put in water, they should not be in contact with water because they catch fire actually. Alkali metals catch fire in water and air. It can combine with the atmospheric moisture also and catch fire. So these are stored in kerosene oil. Now reactivity with the water. Lithium react with water and produce lithium hydroxide and they liberate hydrogen gas also. Similarly, sodium in water produce NaOH plus hydrogen. Potassium gives potassium hydroxide. Similarly. Then reactivity with hydrogen. Alkali metals, let M be the alkali metals, react with hydrogen and form metallic hydrides of the formula MH. For example, lithium gives lithium hydride. Sodium gives sodium hydride. Potassium gives potassium hydride. In these hydrides, hydrogen atom is in the oxidation state -1. Alkali metals always +1. Now reactivity with halogen. Alkali metals react with halogens and form metal halides. For example, lithium with chlorine gives lithium chloride. Sodium with chlorine gives sodium chloride. Now, the anomalous behavior of the first member, lithium. We told the first member of alkali metal series is lithium. lithium show properties different from the other members of the group. Some of the properties are all alkali metals are soft except lithium. Lithium is harder. It has got high melting point and boiling point. All the alkali metals have low melting and boiling point, but lithium has higher melting point and boiling point compared to the other alkali metal. All alkali metals are very reactive except lithium. Lithium is least reactive alkali metal. Lithium mainly forms covalent compounds, but all other alkali metal compounds are ionic in nature. Unlike other alkali metals, lithium can combine with atmospheric nitrogen and form lithium nitride of the formula Li3N. So these are some of the properties, different properties shown by lithium. Anomalous properties of lithium. In addition to this anomalous property, lithium show similarity with the magnesium. The similarities between lithium and magnesium is due to their similar ionic radii. Both lithium and magnesium are hard. They are hard and light. Harder and lighter than other members of the group. Both lithium and magnesium form mainly covalent compounds. Lithium and magnesium react slowly in water. Lithium chloride and magnesium chloride are deliquescent and they form hydrates having formula lithium chloride 2H2O and magnesium form magnesium chloride 8H2O. So lithium, some of the properties of lithium and magnesium are similar, diagonal relationship.